So these are the examples for 6.6. And remember, we are using the properties that we discussed up here. Okay, so the first one, we're looking for the integral from 1 to 3 of f of x plus 6 dx, and we do know the integral from 1 to 3 of f of x dx is equal to 10. So I don't need to know what the graph of f of x looks like. I don't need to know an equation for f of x because I have this piece right here. Okay, so the integral from 1 to 3 of f of x plus 6, I can use the additive property and split that into, let me switch colors. Can split that into the integral from 1 to 3 of f of x dx. Please use complete notation. You have to have this on here. We'll talk more about what it represents later. Plus the integral from 1 to 3 of 6 dx, okay? And then based on the integral value that's given, I know that this is equal to 10, okay? And then this, so let's visualize this. If this was the function y equals 6, that would be a horizontal line at 6, and the integral from 1 to 3 would be this rectangular region, which has a width of 2 and a height of 6, so that is just a 12. So we get a total integral value of 22. Okay, for this one, we're looking for the integral from -2 to 5 of 3 times f minus g, and we're given a few different things. Pay attention to the limits here, okay? So the first thing I'm going to do is I'm going to break this apart, and I'm going to write this as the integral from -2 to 5, I'm going to write it as 3, factor that 3 out, times the integral from -2 to 5 of f of x dx, minus the integral from -2 to 5 of g of x dx, okay? 3 is a coefficient, and then the integral from -2 to 5 of f, so let's see what we have. We know the integral from -2 to 3, and the integral from, okay, so this, notice this is from 5 to 3, okay? So I'm going to, and you don't always have to write all of this out, but I'm going to go ahead and do that since this is the first one I've done like this. So this is 3 times, and I'm going to split this from -2 to 5 as the integral from -2 to 3, and then the integral from 3 to 5. So integral from -2 to 3 of f of x dx plus the integral from 3 to 5 of f of x dx, okay? And then I still have, and then this right here, let's go ahead and plug its value in. We're given that that is -4, okay? All right, so we have 3 times the integral from -2 to 3 we're given is 6, plus, and then here I want the integral from 3 to 5. I have the integral from 5 to 3. If I want to write this as the integral from 3 to 5, remember we said we can flip the limits, but we have to put a negative out in front. So this is going to be equal to the opposite of 3, so -3 here. Okay, and then we still have, now that becomes a +4 at the end. So 3 times 3, 9 plus 4, so this is a total of 13. Okay, another example here. Sorry, these letters are pretty small, but I've got A, B, C, D, and E are the x coordinates along that function, the x-intercepts there. And then we are told that the integral from C to 0 of f of x dx is equal to 3. Let's go ahead and put that in our graph, actually. So C to 0 would be this region right here. So that is a 3 right here, just in that little shaded region. Okay, so first one, we're looking for the integral from 0 to E. So from 0 to E covers these two regions. We remember the definite integral subtracts area below the x-axis. So this is represented with a -7 plus 10, which is a net value of 3. Again, area above minus area below. And then for part B, the integral from B to D. So from B to D is, so we're subtracting the 5 and 7, so -5, and then we're adding 3, so plus 3, minus 7, so that is -2 minus 7, so -9. It is okay to have a negative value because remember we find net area. For this one right here, the integral from a to 0, of the absolute value of f of x. So get rid of my scribbles here. Let's put a 3 in here. The absolute value of a function takes anything below the x-axis and flips it up. So essentially I'm looking at this right here, and that has a value of 15 plus 5 plus 3, which is 23. Okay, and then a little bit different here. This is the integral from a to 0 of f of x dx, and then the absolute value of that whole thing. So we already, no, we have not done a to 0. Okay, so a to 0 has a value, the integral of, let's see, 15. So it's absolute value of 15 minus 5 plus 3, which is absolute value of 13, which is 13. Okay, and notice the difference between C and D. Over here, we took the absolute value of the function and then integrated it. Here, we integrated the function, meaning we found the net area, and then we took the absolute value of that. Okay, so pay attention to order of operations, work from the inside out. This one also has absolute values on it. Here we're going from, I know this is really small, we're going from negative e to e. Well, I don't actually know anything about negative e over here, but I do know that putting absolute value bars on the inside of a function takes the function and reflects it horizontal. Anything that is negative gets reflected on the positive side. So essentially, I could write this as the integral from, when x is positive, it's the same, so from 0 to e. I'm going to put it on the right, though, to show you what I'm doing here. So plus the integral from 0 to e of f of x dx. And then over here, from negative e to 0, instead of putting those negative values in, I would be putting the absolute value of them in, which is the exact same thing as what I have over here. So really what I have is another 0 to e of f of x dx, or twice the integral from 0 to e of f of x dx. Think about a number. Let's say that we had like a negative 2. Okay, I don't know where negative 2 is. Maybe right here. Okay, or no, sorry, positive 2. So let's say we're plugging in a negative 2. Okay, well, if I take the absolute value of that first, then it's right back over here, and this is the y value that gets plugged in. Okay, and that would happen for all the values from 0 over to wherever negative e is. I get the same output as what I have over here on the 0 to e side. Okay, so essentially I have 2 times negative 7 plus 10, which is going to be 6. Okay, and then for this last one, let me slide over a little bit here. So we're going from negative c to negative a. Let me get rid of some of this scribbling. Oops, I need that 3. Negative c, or I guess I don't. It's from negative c to negative a of f of negative x. Okay, putting a negative on the inside of the function flips it horizontally. Okay, flips it across the y-axis. So this is the same thing as the integral from, well, if I take any value from negative, so negative a is, I don't know, somewhere about right here, and negative c is somewhere about right here, but I'm plugging in the opposite of those, well, then I'm right back over here with the integral from a to c. Now, negative c to negative a would be going from here to here, so I instead want to integrate over this interval from a to c of f of positive x. Okay, and then that is 15 minus 5, which is 10. Okay, last example here. Evaluate the integral from 0 to 5 of f of x, where f of x is this piecewise function. So we're going to do this geometrically by looking at the graph. So when x is less than or equal to negative 3, our function is negative 2x plus 7. I'm going to plug 3 into that, so I get negative 6 plus 7 is 1. So I have a point at 3, 1, with a slope of negative 2, or y-intercept of 7. Let's see, 1, 2, 3, 4, 5, 6. This does go up to 7. Okay. So I have a linear segment there, and 4 when x is greater than 3. So 1, 2, 3. So this is 4. I have an open circle here with an arrow going this way. Technically, I guess that's an arrow as well. Okay, so looking geometrically at this, I am looking for the area of that trapezoid plus this rectangle, and we need to go the integral from 0 to 5. So we're going to stop here. 1, 2, 3, 4. We're going to stop here at 5. So I have the area of the trapezoid plus the area of a rectangle. Okay, so the integral from 0 to 5 of f of x dx is the same as the integral from 0 to 3 plus the integral from 3 to 5. It does not matter that we have a point of discontinuity here, because we could split it into two separate integrals, and then that jump there wouldn't even matter. So it's the area of the trapezoid. So let's see, base is 1 and 7 with a height of 3. So 1 plus 7 over 2 times 3. And then plus the area of the rectangle, which is 2 by 4. So I end up with 8 over 2, so 12 plus 8, which is a total of 20.